All right, good morning. Today we're going to talk about the following topics, namely what's written here, i.e. linear algebra, which is a topic of great importance in computer science. Actually, it's true. I mean, really, so linear algebra is a super important topic. A little bit boring, but super important. Basically, you know, like all of computer science research these days, like optimization, machine learning, and like that stuff is all linear algebra. Actually, I bring it up because, well, we bring it up because also the next two topics we're going to talk about, Markov chains and quantum computation, they're also like very heavy on linear algebra. So today is a good day to remind ourselves a little bit about linear algebra. So as always, we're going to try to take a little bit of a computer science perspective, despite it being a math topic. And of course, normally you get like a whole year's worth of course on this, so we cannot cover it all in one lecture, but we'll say a few things. Well, linear algebra is about vectors, and a vector concretely looks like this. It's like a stack of numbers of any height, and the number of numbers that you stack together, or the length of this, or height of this thing, is called the dimension of the vector, which you might call n. And in linear algebra, the numbers are called scalars, just for fun. And they can actually be from any field. So just like you know, when we talked about polynomials, and we said, actually, when you have a polynomial, the coefficients, they like to be numbers in a field. Totally exact same thing in linear algebra. You can do linear algebra where your basic set of numbers is any field. We'll often, but not always, be talking about the real numbers. That's like the most popular field for doing linear algebra. So these are all examples of real numbers. And just to remind you of some notation, if you have a field f, then the set of all vectors of dimension n, or height n, where the numbers are from the field f, is written f to the n. So this is an example. For example, this vector is in R to the 3, R3, good old space. And we particularly like it when the field is the real numbers and the dimensions at most 3, because then you can draw pictures, or at least I can attempt to draw pictures in PowerPoint, which does not always go over, but we'll see. OK, so you typically, here's R3. These are trying to be the coordinate axes, like this one, and this one's like going into the back of the board, or the slides. And you often picture a vector, these stack of numbers, right? Well, it's kind of like a point. But you also picture it as a vector, an arrow going from the origin to that point. So this is like a picture of the vector 7, 5, 2, sitting in R3. I hope you've seen like a little bit of this stuff here in college or in high school or what have you. OK, so in linear algebra, your basic objects are vectors, and the key operation that linear algebra is all about is taking linear combinations of vectors. So what is a linear combination of vectors? It's just like you multiply the vectors by some scalars, and then add them together. OK, so multiplying by a scalar is like stretching, or shrinking, or reflecting a vector. And adding them is, adding them entry-wise, which corresponds to, like following two arrows in a row. So if we have these three vectors in R3, 3, 2, 1, 4, 3, 1, minus 1.5, whatever, this is a classic example of a linear combination of them. 2 times this one, plus 1 times this one, plus 2 times this one. OK, and that gives you another vector. And that's our favorite thing to do with vectors. OK, so let's actually do some pictures in R2. Here, I think I can genuinely draw things well. So here are two good old vectors in R2, u and v. I didn't actually say what their coordinates were, but it's just for illustration purposes. So let's look at some linear combinations. Now, if you just have one vector, you can still take a linear combination of it. It has nothing to add itself with. So the only thing you can do is multiply it by a scalar, or scale it. That's why they're called scalars. So this vector is 1.5 times u. So it's u stretched to 50% more of its length. And this is an example of 0.7 times v. It's like 70% of the length of v. And then I can add these two yellow vectors together. You follow this one, and then you follow this one. And the sum is this point, or vector up here. And this overall vector is the linear combination 1.5 times u plus 0.7 times v. OK, so this is the basic operation of taking combinations of vectors. And we can see some more. We could also multiply vectors by negative scalars. This is negative v. It just reflects it through the origin. And if I added negative v to 1.5u, then it would be like doing this vector and then this vector from the tip, and it would get me out here. So that's the linear combination 1.5u minus v. So this big bright yellow vector and this bright orange vector are both linear combinations of u and v. Do you all know like all the possible linear combinations of this u and v? No. If you look at all possible linear combinations of u and v, you can get this yellow one. You can get this orange one. Yeah, you can get all vectors in R2 as linear combinations of this u and v. If you take them appropriately. Hope you've seen that before. OK, let me make a remark here. As I said, we mostly stick with the reals because it's easier to draw pictures. But we will sometimes talk about linear algebra where the field, the numbers, are not the reals. So one field that we talked about before is the integers mod 11. Numbers you can add, subtract, multiply, and divide. And you can look at vectors of height 3 where the entries are from integers mod 11. And all of, everything I'm going to say is still kosher in this setting. But you should still, it's very helpful still to always maintain the intuition you have when it's just good old real numbers and real space. OK, so I kind of want to actually give you some notation for linear combinations of vectors since it's going to be our favorite thing to do with them. So say you've got two vectors like 3, 2, 1 and 4, 3, 1. And you want to take linear combinations of them. One good thing you can do is stick them together and make them columns of a matrix. So this is a matrix with 3 rows and 2 columns. It's the numbers inside this square box. And this is kind of like a definition. If you want to take the linear combination where you do A copies of 3, 2, 1 and B copies of 4, 3, 1, you just write it like this. OK, so this really means that you should do A copies of 3, 2, 1 and B copies of 4, 3, 1 and add them up. Now, this is also what's known as multiplying a matrix times a vector, which I also hope you remember at least the little algorithm for doing. But it really just means this. I mean, take this linear combination of these 2 columns. OK, so this is one way you can define what it means to multiply a matrix by a vector. And notice, of course, that you need the number of rows, entries in the vector, to be the same as the number of columns in the matrix. And we can extend this to get a definition of matrix times a matrix. And one thing we'll often do is we have a couple of fixed vectors like these 2, and we'll be interested in several different linear combinations of them. And in that case, you can just stack the linear combination coefficients that you're interested in into columns. And that gives you matrix multiplication. Let me give you an example. Hopefully, you can kind of see the colors. So if we're interested in linear combinations of 3, 2, 1 and 4, 3, 1, and we're interested in 4 different such linear combinations, the one where you have coefficients 1, 0, 0, 1, 1, 1, and 100 minus 2, well, the resulting columns tell you what those linear combinations are. So of course, if you take 1 copy of the first row and 0 copies of the second row, you get 3, 2, 1. If you take, let's say, 100 copies of the first row and minus 2 copies of the second row, you get this 292, 194, 98. OK, so this is one way you can think of what it means to multiply 2 matrices. OK, it's just taking a bunch of linear combinations of columns of the first one. And again, clearly, the number of columns in the first matrix has to equal the number of rows in the second matrix. OK. We'll be doing some matrix multiplication. I want to remind you or tell you that matrix multiplication is associative, which means if you have 3 matrix multiplies in a row, it doesn't matter where you put the parentheses. But it's definitely not commutative. I mean, you cannot, if m and n are matrices, then m times n is not n times m. It doesn't even type check, right? I mean, you could not multiply this matrix on the left of this matrix, because the number of rows and columns doesn't match up properly. Okay. So as we've seen, if we have some matrix like this 3, 2, 1, 4, 3, 1, then for every length 2 vector of coefficients, it gives you a new length 3 vector, the one that's like the appropriate linear combination of these two columns. So if you want, you can sort of think of this matrix as a function or a mapping that takes as input a length 2 vector and spits out a length 3 vector. Okay, so this matrix also corresponds to a function that maps length 2 vectors to length 3 vectors. You give it like the coefficients of a linear combination, it tells you what that linear combination is. So it maps 1, 0 to 3, 2, 1. It maps 0, 1 to 4, 3, 1. It maps 1, 1 to 7, 5, 2, etc. Okay, so this is another good way to think of what a matrix is. It's a transformation that maps, vectors to vectors by what coefficients they are to what linear combination it gives. Any questions so far? Okay. So let's do, we hardly did anything, but we can still do an application. So let's do an application to like a popular topic in computer science and recreational math, the Fibonacci numbers. Okay, so usually you see the Fibonacci numbers maybe in computer science when you're trying to learn like what recursion is or how to write a little loop. We'll also see how it's related to linear algebra. So probably you remember what they are, right? It's a sequence of numbers. You just start with 0 and 1. And then the next number is the sum of the previous two. So like 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, etc. Okay, so it's amusing to list out these numbers. You can write it more formally or recursively like this. We have a sequence, f sub k. The 0th one, f0 is 0. The next one, f1 is 1. And then the remaining ones are given by this recursive rule. Fk is fk minus 1 plus fk minus 2. Now, this is how it's usually defined. And if I said to you normally, like, OK, what is the 100th number in the Fibonacci series sequence? Well, it looks like you have to do this like 99 times, or 100 times. Just keep calculating them until you have a list of 100 that goes all the way like that. But actually, there's a direct formula, if you want, for fk, the kth one. Like, you don't have to calculate all the preceding ones. It's just this. That's the formula. And it looks, if you've never seen it before, it looks a little bit crazy because like the Fibonacci numbers is like a list of positive integers. But this formula, it's got like subtraction, it's got exponentiation, it's got fractions, it's got like √5, which isn't even like a rational number. So if you haven't seen it before, it's kind of crazy that this formula gives you this sequence of numbers. And if I told you that and then say, OK, prove it, well, how would you prove it? Induction, yeah. You would do it, too. It's not that hard. You do the induction. It's going to work out. But you might ask yourself, but how would you come up with that in the first place? That's less clear. So I guess there's probably more than one way you could come up with this. But let me tell you the linear algebra way, which is how I normally would think about it. So how are we going to come up with this formula using the power of linear algebra? Well, there's the definition of the Fibonacci sequence again. And the key idea of it is in order to get like the next number, you only have to remember what the last two numbers were. OK? So if you're trying to keep track of them, you sort of only need to remember the last two numbers in the sequence. So let's imagine stacking the last two Fibonacci numbers into a vector. It'll be more clear what I mean in a second, hopefully. Let's say you're going along and you've computed up to the k minus first Fibonacci number, and you have fk minus 1 and fk minus 2, and you put them in a little vector of height 2. Now, how do you get to the next last two, fk and fk minus 1? Well, it's right here by the rule. This entry, whatever it is, just shifts down one to here. And this one is the sum of these two. So actually, each of these new entries in the sort of last two vector is a linear combination of the previous two numbers. Well, let me just say it like this. This is like a true relation. Here we have a vector of height 2. This is a matrix, a 2 by 2 matrix. And if you multiply this matrix by this vector, you get the next two numbers. right? Because this says take fk minus 1 copies of 1, 1 plus fk minus 2 copies of 1, 0. So in the first row, you'll get the sum of them. And in the second row, you'll just get the top one here. Okay, there's nothing too tricky going on here. If you just remember how to multiply matrices and vectors, you see that this is a valid formula. So it tells you if you have a little vector that stores the last two numbers, you multiply it by this matrix, you'll get like the next last two numbers. Let me just give you a picture here. So the first two numbers in Fibonacci sequence are just defined to be 0 and 1. So we put 0 and 1 in a little vector. If I multiply it by this, I get the next two numbers. Well, 1 and 1. If I multiply by this matrix again, I get 2 and 1. If I multiply 2, 1 by this matrix, I get 3, 2. If I multiply again, I get 5, 3. If I multiply again, I get 8, 5. So this is the sequence showing up, like 0, 1, 2, 3, 5, 8. Okay, and like this vector, as you multiply by this special yellow matrix, we're going to be very obsessed with this yellow matrix. As you keep multiplying it by it, it kind of keeps giving you the next last two numbers in the series. So, we've just taken the basic definition and transformed it into like linear algebra language. And now we're kind of curious, like what happens if you start with the first two numbers, 0, 1, and you just keep multiplying this yellow matrix by this yellow matrix. Like that'll give you all the rest of the numbers. Maybe we can use this to our advantage. Any question about that? You see what's going on? OK, so in particular, we started with 1, 0, and we just multiplied by this yellow matrix 5 times. It's like we did this matrix to the power of 5 times the initial number, and we got to 8, 5. OK, so in general, if we start with this vector 0, 1, the initial two numbers, and we multiply on the left by this special yellow matrix k times, then we'll get the kth Fibonacci number and the k plus first Fibonacci number. OK? Good. So remember I told you can think of a matrix as a map. It takes as input a vector, it spits out a vector. And here it's a 2 by 2 matrix, so it takes in a 2-dimensional vector and spits out another 2-dimensional vector. So some kind of transformation that takes vectors to vectors. And we're interested in multiplying by it repeatedly. So we're kind of curious what happens when you take a vector and do this transformation to it like many times in a row. So how can we figure out what this map looks like? Oh, this is a good job for a computer. So I will actually show you a little demo, tiny one. If you ever have vectors or matrices, you should always just use MATLAB to solve all your problems. You can use it for free at Carnegie Mellon. So that's what we'll do. So let me go to it. So we're interested in this. I don't know if you can read this, but you'll see it soon. We're interested in this matrix A, which is like 1, 1, 1, 0. OK, now MATLAB, there it is. That's A. Now MATLAB has this handy thing that helps you look at matrices. OK, so let me explain what's going on here. This is just a picture of R2. It's like the horizontal axis and the vertical axis. And what this little app in MATLAB does is it lets you like kind of take a vector, like this green vector x, and it shows you what is A times x. And it actually always starts out, luckily for us, with the vector that we care most about, 1, 0, because that's the first one we apply A to. And you see AX is the blue one. It's telling you if you do AX times 1, 0, you get, that's 1, 1, which is right. That's like the next set of consecutive Fibonacci numbers, 1, 1. OK, and so we can just imagine like what happens, and I'll show you. You can move x around and see where AX goes to. Now, there's one little annoying thing with this applet, which is that you can't put x anywhere you want. It only lets you put it to like length 1 vectors. So it's not really a big problem because these transformation by matrices have the property that if you do like A times 5x, it's the same as doing 5 times AX. So kind of like, if you scale a vector and then hit it by A, it's the same as hitting it by A and scaling it. So you can kind of assume without loss of generality to get the picture that you're always applying it to a length 1 vector. So for example, the next thing you would do is you'd apply A to this 1, 1 vector. I can't do that because 1, 1 is a vector of length square root 2. But I'll just put x into that direction, and it'll tell me at least the direction that ax would point to. So that looks like this. OK, so now x is the green thing. And you see that if you multiply it by a, it kind of goes a little bit in that direction. Which makes sense. If you apply it to 1, 1, a gives you 2, 1, which is kind of twice as long in this way as it is up in this way. So actually, the next thing you might do is say, OK, if I want to multiply a again against this, I'd consider moving the green thing to where the blue guy is now and see what direction that points in. So let me do that. It'll kind of shoot it out that way. And then if I move the green to where the blue is again, it would like shoot it out that way. And actually, you see, if I just keep doing this for a while, like if I keep multiplying by a, it'll sort of move more and more in that kind of diagonal direction. And actually, the current x I show up here is very interesting. It's an x that has the following interesting property. When I multiply a against that x, it doesn't like twist x or rotate x or anything. It just stretches it. That's a very interesting property that we're going to pay attention to. This property that x has, namely that when you multiply by a, there's no rotation or anything. It just stretches it. It just scales it. So that's an example of such an x where it just scales it. Now we can look at to see if there are any other directions like that. And actually there are. If you put x over here, you might not realize it at first, but this green x, when you multiply it by a, it turns into this blue vector. And that's actually just a scalar multiple of x. It's a negative scalar multiple because it reflected it. And it got about 60% as long as it was before. So this, if you take this x, multiply it by a, you get like about negative 0.6 times x. And again, that's a special direction where there's no rotation. It's just, well, there's a reflection and scaling. So there's scaling by a negative number. Any questions about this? You see that that happens? So we can draw the rest of it and get like a little thing that looks like Saturn. So this is how it works. Ooh. OK, that's good to know. I mean, in general, if you multiply in 2 dimensions by a matrix, right, it like scales the vector some amount and also kind of rotates it. OK, and we're going to ask you to pay attention to these 2 special directions. This one, which is actually sort of the same as this one, just in the opposite direction. And also this one. These are both the directions where if you multiply a times that vector, it just scales it. OK, so let me go back to PowerPoint now. OK. So this is what we were looking at. And yeah, what I wanted to say is these black vectors are pointing in these special directions wherein a just scales things. And I'm interested in figuring out what these directions are. OK, like literally what the numbers are for these black vectors. And I can just solve for them pretty easily. And that's what I'm going to do now. You see, to solve for them, I'm interested in a vector xy such that when you do this matrix times xy, you just get a scalar multiple of xy. So lambda times xy for some scalar lambda. Now, I'd like to solve for this and hopefully get out those 2 black vectors. Now, there's a bit of an issue, which is that, oh yeah, by the way, if you look at the picture, the lambdas are about 1.6 and about minus 0.6. Now, if you write this out, you actually get 2 equations and you have 3 unknowns. So it looks like you have a bit of a tricky situation on your hands. But it actually kind of makes sense. The thing is, there's something that's sort of not unique about these vectors x, y, which is that if you have a solution to this, a vector x, y, which a just scales, then also like 2 times xy and 3 times xy and a quarter times xy all have these properties. I mean, if you take a vector, any scaling of it also has the property that if you take a vector that satisfies this and you scale it, then that vector will still have the property. So we have to like sort of arbitrarily scale this vector in some way. And what we're going to do is just whatever it is, we're going to imagine scaling it until the second coordinate is 1. OK, so maybe you didn't quite follow what I said, but I want to say that without loss of generality, in trying to solve this equation, we can just fix y to be 1. It's like in this picture, I drew these vectors just so that their height was 1. I mean, I could have drawn them any height. So in any case, let me do that. Let me say I'm trying to solve this equation, and this system, and now I have two variables and two unknowns. So if you just multiply it out, you see the first entry of this product is x plus 1, so that should equal lambda x. The second entry is just x, so that should equal lambda. And now you have this little system. It's very easy. You can just say that lambda equals x, so plug it in here. You get x plus 1 equals x squared, or x squared minus x minus 1 equals 0. So now you have to solve this one equation of one unknown, or find the root of this polynomial, which you can do using the quadratic formula. And finally, you get that the solution is x and y are both 1 plus or minus root 5 over 2, which maybe looks familiar to you. OK, so long story short, in this example, let's look at these two values, 1 plus root 5 over 2, which is about 1.6, and 1 minus root 5 over 2, which is about minus 0.6. This number is sometimes called the golden ratio. And I'll call them phi and psi. And what we just showed is that if you do phi 1 and you multiply by this matrix, you just stretch phi 1 by phi. That's literally what we showed. And if you do psi 1 and multiply by this matrix, you stretch psi 1 by psi, which is like stretching it by minus 0.6. And you don't need to know this, but these interesting directions happen to be called eigenvectors. That's the math name. And these scaling factors happen to be called eigenvalues. That's the math name, but we won't use that terminology in this class. In any case, so there they are. This is about like 1.6 comma 1, and this is about minus 0.6 comma 1. And this is very convenient, because this says if you take one phi and you multiply this by this special matrix, it just stretches by phi. And it's still in the same direction. So if you multiply it by this matrix again, it just stretches it by phi again, because it's still in the same direction. Every time you multiply it by this matrix A, it just keeps stretching it in this direction by a factor of 1.6. So for example, this vector is about 1.6 comma 1. You see, if you multiply it by, this is, on one hand, it's multiplying it, just scaling it by a factor of phi every time. But it's also, it's multiplying it by this matrix, so it's doing the Fibonacci thing. This is exactly what would happen if you did the Fibonacci series, but starting with 1 and 1.6, 1/8, instead of starting with 0, 1. Because like this is the sum of these two numbers, this is the sum of these two numbers, etc. Right? This number is exactly the number such that multiplying phi by itself is the same as doing 1 plus phi. OK, and similarly, it's the same thing with psi, negative 0.6. If you started your Fibonacci series a little strangely with 1, and then the next one was minus 0.6, then the next one would be 0.38, the next one would be minus 0.236, etc. But this is also the same as just taking this vector and repeatedly scaling it by a factor of minus 0.6. So it's repeatedly reflecting and also shrinking by 60%. So actually, this gives us, if for some weird reason we decided to start our Fibonacci with 1 and phi, then there would be a very simple formula for the numbers in the series. It would just be the powers of phi. Of course, we don't, the classic Fibonacci starts with 0 and 1. So what we really want to know is like what happens if you multiply 0, 1 by this matrix A many times. And I kind of try to show you the picture that eventually starts pointing in the direction of phi comma 1. So the way we can conclude is we need to take this vector 1, 0 that we care about the most, and what we want to do is write it as a linear combination of these two vectors. I told you, one thing we always want to do in life is take linear combinations. So we're interested in this red vector, and you can pretty easily see that if you subtract this vector from this vector, it goes in that direction. And it's like a half plus root 5 over 2 minus half minus root 5 over 2. So you get root 5, 0 if you do the subtraction. So long story short, if you take this linear combination of these two special black vectors, 1 over root 5 and minus 1 over root 5, you get the red vector that we care about, 1, 0. So the vector that we really want to start with, 1, 0, is this linear combination of the two special directions. And now, this is going to be the last slide. We're kind of done. Remember, if you start with 0, 1, and you multiply by this matrix A k times, you get the kth and the k plus first Fibonacci number. And we saw that 1, 0 is this linear combination. So we can plug that in here. And now we know that these special vectors have the property that, multiplying them by the matrix A k times is just the same as scaling them by, in this case, phi, and in this case, psi, k times. So this is why we get phi to the k and psi to the k. And now we're in good shape. I mean, if you imagine just calculating what this is, in the second entry, you'll get 1 over root phi times phi to the k minus 1 over root phi times psi to the k, and that's fk. So in conclusion, that's how you get this formula for the kth Fibonacci number. It's all due to the glory of linear algebra. Any questions about that? All right, well, you can take a look at it more carefully in the comfort of your home. So since we love linear combinations so much, let me talk about them a little bit more. So as you saw in this interesting application, a key step was taking our favorite vector 1, 0 and expressing it as a linear combination of these two other fixed vectors. And more generally, what we often do in life is fix a small number of vectors and ask ourselves, which other vectors can we get by taking linear combinations of them? Or if I have a third vector, can I get it by taking linear combinations of the other ones? So let's make a definition for this. If I give you a set of vectors S, v1 through vk, then their span is the set of all linear combinations of vectors in S. So usually S is finite at some small number, but actually, let's say if you're working over the reals, there's infinitely many vectors in the span. I'll show you pictures in a second. And we can use matrix notation to express this. Where the span of, let's say, v1, v2, v3 is this. It's everything that you can get by stacking them into columns and multiplying by a vector of coefficients from your field. As a small technicality, if k is 0, then you're taking linear combinations of 0 many vectors. But you know that whenever you add up 0 things, it's 0. So small technicality, span of the empty set is the 0 vector. I hope you will remember that. OK, so let's do a picture, let's say in R3, our favorite space for pictures. So let's go back to this vector we like, 7, 5, 2. If I ask you, what is the span of just the set that contains this one vector, what would it be? No, the span of a set of vectors is in general another set of vectors. Those are all the vectors that you can get by doing, well, linear combinations of just this one vector. Set of all points on the line? Yes, that's right. I mean, if you only have one vector, then you're only multiplying it by a set of coefficients of height 1. It's really just like you can scale that vector by any amount you want. So the set of all, it's kind of a bit degenerate, but the set of all linear combinations of this one vector is just all the scalings of that vector. So it's all the things on this line through the origin. OK? Say I give you another vector, 3, 4, 1. Does anybody know what the span of these two vectors together is? What it looks like, at least? Yeah, it's like a plane. If you imagine adding up these vectors in space with multiples and stuff, they'll always be on this plane, like it's hard to draw, but like if these are like rods in space and like you took a big piece of paper and kind of lay it on them, that would be the plane spanned by them. Okay, if you add up any combinations of these vectors, it's always going to sit in this like two-dimensional plane through the origin. Okay. Now let me try to mess with your mind a little bit by doing just another example, but I'm going to change the field. I'm going to take us out of our favorite zone of the real numbers and talk about a finite field. Now my favorite finite field, and yours too, is the one with two elements. It's great, right? There's just 0 and 1. It's the integers mod 2. There's not a lot to worry about. So let me just remind you, F2 denotes the field with two elements, the integers mod 2. It's just 0 and 1. And F2 to the n is all the length n vectors where the numbers inside the vectors, the scalars, are just from F2. So unlike when the field is R, there's actually only finitely many vectors in the whole world in this scenario. How many such vectors are there? 2 to the n, yeah, because you have n slots and anything can be, each one of them can be 0 or 1. So like F2 to the 7 is just the set of 128 different vectors. And this is an example of a linear combination of them. Here's one such vector. Here's another such vector. My coefficients I chose were 1 and 1. So I do 1 times this plus 1 times this. And everything is mod 2. So in particular, this is the answer. OK, so you know, it makes less sense geometrically, but I mean, all the definitions still apply. And actually, over F2, when you're working with the field being F2, linear combinations are particularly easy because, you know, a linear combination is defined by its coefficients, right? The coefficients can either only be 0 or 1. So that simplifies things. I mean, if you multiply a vector by 0, you may as well just delete it. And if you multiply by 1, it's like you don't change it. So in general, if you have like 5 vectors in F2 to the n, doing a linear combination of them, which is like adding them up with coefficients of 0 and 1, is exactly the same thing as just adding together a subset of them. Right? The ones that you put coefficient 1 on. OK, so let me give you an interesting example of a span. So here I'm working in F2 to the n, vectors of height n. The entries are 0 and 1 mod 2. And here are n minus 1 vectors. If you take a look at these vectors, there's a 1 in the last entry of all of them. And otherwise, you get like a 1 in the first coordinate, a 1 in the second coordinate of the second, a 1 in the third coordinate of the third, all the way down to a 1 in the n minus 1th coordinate of the n minus 1th vector. So now, what I want you to tell me is, how can you describe the span of these vectors? What is a good description of the span of those vectors? I will take a drink while you think about it. Okay, so what is all linear combinations of these vectors? Mod 2. We've got a lot of good ideas. I think this person down here had his hand up.
So I had all of the points in the plane xn equals 1.
Pardon me?
All the points in the plane xn equals 1.
You're saying like all the vectors that have a 1 in the last coordinate? No, that's not correct. And I'll give you a reason why. One thing that's in the span of these vectors is just 1 times the first one plus 1 times the second one plus 0 times the rest. So if I do 1 plus the first one, 1 times the first one plus 1 times the second one, I'll get 1, 1, 0, 0, 0, 0, 0. And here I'll get 1 plus 1, which is 0 mod 2. So I would get 1, 1 followed by all zeros. So that doesn't have a 1 in the last entry. But it is an example of a vector that's in here. 1, 1 followed by all zeros is in the span. Yeah?
Either all vectors with an even number of ones and the last one 0 and an odd number of ones and the last one. Or the other way.
Yes. What you said is true. And I could say it even more Is there an even simpler way to say it? Yeah?
Did you just say the last element is the parity of the previous bits?
Yeah, that's another way to say it. Kind of like what Apurva said. The last entry, any vector where the last entry is the parity of the previous ones, or even, yes?
It's the sum of all the previous ones?
Mod 2, yeah. Yeah. Yet another way to say it is it's all the vectors have an even number of ones. So why is that? I mean, everything that you said was correct. Right? Because basically what happens if you do a linear combination of these things, like I said before, when you only have two coefficients, 0 and 1, it's just the same as adding up some of them, like a subset of them. So if you see, if you're adding up a subset of them, you can kind of get whatever you want in the first n minus 1 coordinates. But you'll always get, if you take 7 of these vectors, you'll always get 7 ones in the bottom, which is 1 mod 2. So the last entry, as was said by a couple of people, will always be like the sum, mod 2, of the entries in the first n minus 1 spots. So if you take an even number of columns, you'll get an even number of ones up here and then 0. And if you take an odd number of columns, you'll get an odd number of ones in the first n minus 1 coordinates and then 1. So in either case, you'll always get an even number of ones. Okay, so that's also an example that you can think about a little bit more in your spare time. So let me go back to, let's get a little away from this F2 stuff and go back to this picture with the reals. So we saw if you took these two vectors and you took their span, it gave you like a two-dimensional plane through the origin. And what's interesting is that this is kind of like a copy of two-dimensional space, like two-dimensional vector space. It's like tilted, this sheet of paper, but it still kind of looks like two-dimensional space, just sitting in 3 dimensions. And we're going to kind of make that a little bit more formal. We kind of want to express this notion that this two-dimensional plane through the origin is like it's a set of vectors that all like hang out together in a two-dimensional space. So what do I mean by this? So here's a definition. It's our definition of what is a vector space or a vector subspace. In this class, I'm not going to make a big difference between these two terms. So like they're all the same thing: subspace, vector subspace. And it's just the span of a bunch of vectors. That's it. So if you have, in general, you're starting with n-dimensional vectors. You take some collection of them S, and you look at their span. I call the resulting set a vector space or a vector subspace. Okay, and so a good example to always keep in mind is this two-dimensional piece of paper sitting in 3 space. And in particular, the reason why it's kind of called a vector space or a subspace is a set of vectors is a vector space if it's closed under linear combinations. So whenever you have a vector space like this, the span of some vectors, it has the property that whenever you take some vectors in it and do a linear combination, you stay in that space, right? So it's like, the simplest case in 3 dimensions is like the flat copy of R2. It's like this tabletop, and if you have some vectors sitting on the table and you do linear combinations of them, they stay in the table, right? Even though there's this third dimension that they don't know about going up here. Okay, so let me give you some examples. And we'll start with one we just saw. This set E, the set of all vectors with an even number of ones, is the span of a bunch of vectors. So it's a vector space, or a vector subspace. And actually what I told you is that meant that it's closed under linear combinations. If you take any, let's say 2 vectors that have an even number of ones and add them up, you get another vector with an even number of ones. Remember, this is all mod 2. And the reason is, well, you have an even number of ones in the first vector, an even number of ones in the second vector. When you add them, kind of collectively, you have an overall even number of ones. Now, sometimes you take 2 ones that you added up and they change to a 0 because you're working mod 2, but it still preserves the fact that you have an even number of ones. Well, we'll do an even simpler example. Let's look at these 3 vectors. in 3 dimensions, 1, 0, 0, 0, 1, 0, and 1, 1, 0. It has 3 vectors in 3 dimensions, u, v, and w. How would you describe the span of these 3 vectors? All their linear combinations. Yes?
All vectors whose z-coordinate is 0.
Yeah, it's all the vectors. This is actually like what you said. Yeah, all the vectors whose third coordinate is 0. Because if you do like multiples of these vectors, you'll still have 0 in the last coordinate. You add them up, you'll still have zeros in the last coordinate. And also you can get any vector that has a 0 in the last coordinate. Like if you want to get like 3, 10, 0, just take 3 copies of this, 10 copies of this, 0 copies of w. So indeed, T, it's like the tabletop, is all the vectors that have a 0 in their third coordinate. So in pictures, here's v, u, v, and w. This one is like sitting flat on the floor. This one, it's hard to tell. And their span is like all the linear combinations. It's like all the things on the floor. You know, it's all the things with height 0. And this is a subspace. It's also like a 2-dimensional piece of paper. Now, it's actually also the span of any 2 of them. It's not hard to check. To get like all the vectors that have 0 in the third coordinate, you can just do the span of these 2 vectors. You'll still get it. Or actually, if you think a little bit more carefully, it's the span of any 2 of them. Maybe you can see that from the picture a little bit. You can get to any vector on the floor by taking linear combinations of your favorite 2 of these yellow vectors. So what I'm trying to get at with this example is that this set of vectors, u, v, and w, it spans T, but it's a bit redundant because you don't need all the vectors. And we would kind of prefer in life to have sort of an irredundant set in our spans. You know, if you were going to span a space, it's nicer if you do it using the fewest vectors that you can. Okay, so this leads us to our last concept and definition in linear algebra, which is that of linear independence. And it's got a very simple definition. So a subset of vectors S is linearly independent if there's no vector in S which is a linear combination of the other ones. Okay, there's no way you can make, for every vector, there's no way you can make it as a linear combination of the other ones. So let's go back to this example with u, v, and w. So the question I want to ask is this set u, v, and w linearly independent? And actually, before you answer, let me stress a point, which is that linear independence is a property of sets. Okay, it's not a property of vectors. Like if I say this vector is linearly independent, that doesn't make any sense. Okay, it's only sets of vectors that are linearly independent or not linearly independent. Okay, so let me ask: is this set u, v, and w linearly independent? Somebody want to say out loud? No, it's not, because as we saw before, like for example, w, which is 1, 1, is a linear combination of u and v. Okay? So if it's not linearly independent, it's linearly dependent. Okay, what about just the set of 2 vectors u and v? Is it linearly independent? Yes, because it's easy to check. I mean, the only way it would not be is if v was like a linear combination of u, which means that v is a multiple of u and v is not a multiple of u, and vice versa. Okay, so these guys are linearly independent, and so are uw and so are vw as sets. What about just the set with 1 vector in it, namely u? Is that linearly independent? Yes. I'm actually going to get into like the weirdo edge cases, but let's do the weirdo edge cases since we're testing out the definition. Yes, because it would only be linearly dependent if u, 1, 0, 0, was in the span of the rest of them. What is the span of the rest of them? Yeah, this is also a technicality. If you take away u, you're left with the empty set, and the span of that is the 0 vector, the vector of all zeros. But u is not the vector of all zeros, so it's linearly independent. Okay, now let's really dig into the edge cases since we're here. What if you had a set that only had one vector in it, and it was the all zeros vector? Would that be linearly independent? No, because it is in the span of the empty set, so it's not linearly independent. Now we're getting a little annoying, but I bring this up because a linearly independent set will never have the 0 vector in it. That's what I want you to remember. Because 0 is in the span of even the empty set. And lastly, is the empty set linearly independent? Yeah, for like a vacuous reason, but never mind. Anyway, these are edge cases, but I really want you to remember the main case. Like, these are not linearly independent because W is a linear combination of U and V, but let's say U and V are linearly independent. Okay, any questions? Okay, so last definition. So let's say I have a bunch of vectors, S1 through SD. I call that set S. We've talked about two things, like the span, and we talked about linear independence. I will now put them together. So if I take their span, that gives me, maybe like a line or a plane or something, and I'll call that W, and that's a vector space or a subspace. And I'm interested in the case when these vectors are also linearly independent. That's kind of like saying they're like a minimal set which has this span, like there's no redundancy in them. And in that case, we have this very nice theorem that says every vector in the subspace, in the span, is a unique linear combination of the vectors in S. Okay, by definition, if W is the span of these vectors, then every vector in W is some linear combination of the vectors in W in S. But if they're also linearly independent, like they're not sort of redundant, then it's a unique linear combination. And that makes us happy. Let's do the proof. It'll fit into this space. So let's say that you have a vector v, and this is a linear combination of the S vectors that gives you v. So here, S1 through SD are vectors, A1 through AD are scalars. And let's say v is also a different linear combination. Well, it's this linear combination, b1 S1 plus dot 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 bd SD. So what are we trying to prove at this point? What do we want to prove to show this uniqueness result? Yeah, we want to show like the last line of the proof, or actually it's going to be the next line, is that we want to prove that like A1 equals B1 and A2 equals B2, so that they're the same linear combination, right? This is a general life strategy. If you want to prove something is unique, you say, let's say we had two things that have the property, then they have to be the same thing. Right? This is how we're proving that it's a unique linear combination. We're saying, well, if you ever have two linear combinations that give you a vector v, then they're actually the same. Okay, so how are we going to prove this? Well, if they're not all the same, like A1 equals B1, A2 equals B2, etc., then there's some k where they're different. So let's assume that AK differs from BK. And for notational simplicity, let me assume that this k is 1. So A1 does not equal B1. Now I'm just going to subtract these two representations. Subtract this vector equations. And I'll get 0 on the left. And on the right, I'll get A1 minus B1. That's a number, a scalar, times vector S1. Plus A2 minus B2. That's a number times S2, which is a vector, plus dot, dot, dot. And A1 does not equal B1, so this number is not 0. And if you have a number that's not 0, and everything is a number in a field, then you can divide by it. That's what we want to do. So actually what I'm going to do is I'm going to take all this part of the vector and put it on the left-hand side and divide by this number, A1 minus B1. So what do I get? I get that S1, the vector, is a linear combination of the other vectors, S2 through SD. These are all numbers. And then we have a list of numbers times vectors. So S1 is a linear combination of the other S's, which contradicts the assumption that these vectors are linearly independent. It's exactly what the definition says. Okay. Any questions about this proof? Okay, so when you're in this nice scenario where you have a subspace, which is the span of subvectors, and those vectors are linearly independent, so they're kind of not redundant, and therefore every vector in the W is a unique linear combination of them, we say that this set is a basis for W. So a basis for a vector space is a spanning and linearly independent set. Okay. At this point in the lecture, I was going to prove a theorem in linear algebra because it's actually the most interesting first theorem in linear algebra. It's like a non-trivial theorem about linear algebra, but I'm actually going to skip it in the interest of time. I'll tell you what it was, though, and you can look at the slides later. Let's say you have a vector subspace. The theorem is that every basis for it has the same number of vectors, and that's called the dimension of the vector space. It's like saying, again, imagine you're in 3 dimensions, and you take a vector space. That's the span of some vectors. So maybe you took 3 vectors, but they spanned a 2-dimensional space, one of these pieces of paper. Well, it wouldn't be a basis, these 3 vectors, because they're redundant. And this kind of says, like, there's a notion of dimension. Like, if you have a 2-dimensional, plane in space, every basis for it has 2 vectors. It's kind of, you probably know about this. I mean, it's kind of from your intuition that, in 3 dimensions, you have these 1-dimensional spans, these lines, these 2-dimensional spans, which are like the pieces of paper, the 3-dimensional spans, which is everything. But we're going to skip the proof. But you should take a look at the proof. It's a little bit interesting, particularly because the proof is like an algorithm, as you'll see. Actually, in linear algebra, all the key theorems are, in a sense, algorithms. Like Gaussian elimination is like a key algorithm. This is also proved by an algorithm. But I will skip it. So it goes like this. You can read it really fast. Aha! And we're done. Well, you can try to read it. It's interesting. Okay, I skipped this because, I want to have time to talk about the application. That we'll do at the end. And this application of linear algebra, I like it very much. It's an application to a familiar scenario. Now, if you remember last time, we talked about error correcting codes, and that's what we're going to talk about again in the last 15 minutes. This is a scenario where you have 2 parties, Alice and Bob. They're not worried about any eavesdroppers or secrecy or anything. Alice is just trying to get a message to Bob. Okay, but the trouble is that when Alice transmits a message, it can get corrupted. Okay, like the symbols in it can get corrupted. So Alice wants to add some redundancy to the message so that even if some symbols are corrupted, Bob can still figure out what she or he was trying to send. Now, if you remember last time, we had this very beautiful solution to this called Reed-Solomon encoding. It used polynomials. It was very cool. I didn't tell you there's a little bit of a problem with it. So imagine, this was a scenario from last time. Alice had a message, which is like a sequence of bytes, or we thought of them as numbers in the field, F257. And her message was like D+1 symbols long, and Alice had this cool system. If she was concerned that there could be k corruptions, she treated the symbols as the coefficient of a polynomial, and then she sent the evaluations of the polynomial at P1, P2, up to P of D plus 2k plus 1. And then Bob did some Lagrange interpolation to get the coefficients back, and everything was cool. There's a couple issues with this, though. One is, Alice might be like, wait a minute, what if my message length, D plus 1, plus the number of corruptions is bigger than 257? Seems pretty possible. I mean, the message may well be bigger than 257 bytes long. Then it's a bit of a problem to do this, right? Because these are supposed to be evaluations of the polynomial at this many different points, or different values. But there are only 257 different values, mod 257. So she's actually stuck in this case, or if she or he wants to send a pretty long message. That's a little problem. Another problem is we made the assumption that like when Alice transmits a message, she's like transmitting a sequence of bytes. We made the assumption that the corruptions were at the byte level, that like a byte could get like corrupted or erased maybe. But like what if the channel corrupts bits? Then she's kind of got a bit of an issue. You know, she could do everything mod 2 rather than 257, but then her messages cannot be more than like 2 bits long, which is really bad. Okay, so we're going to get a new and also interesting and pleasant solution to Alice's dilemma using linear algebra. Okay, so let's imagine this scenario. Actually, we're going to simplify it soon enough, but let's say Alice wants to send a n-bit long message to Bob, and she's worried that the channel might flip or corrupt up to k bits. Now, if it's corrupting bits, you know, like a corruption is just flipping a 0 to a 1 or flipping a 1 to a 0. So Alice is worried about that, so how can she get the message across? As always, she wants to maybe add some extra bits to her message as kind of redundancy, so that even if the channel flips some of the bits, Bob can still figure out what she was trying to send. Let's actually even dial down our expectations a little bit. Let's imagine the channel might only flip up to 1 bit. And for some reason, it's going to be convenient notation-wise, I'm going to assume that Alice is sending an n-1 bit message. In fact, let me dial down the expectations even further. Let me just worry about, for now, the question of how can Bob even detect if there's been a bit flip? You know, forget Bob like trying to figure out Alice's message. Let's just say Alice has this n-1 length message. She's worried that there might be a bit flip, so she maybe adds some redundancy. She transmits to Bob. Bob gets like a received string of bits, and he just wants to know, was there a bit flip in here, or is this exactly what Alice sent? Okay, I mean, ultimately he also wants to figure out if there was a bit flip, which one was flipped, but let's warm up with just trying to tell if there was a bit flip. Okay, so let's see a solution to this problem. And here's a classic solution, which maybe you've even thought about before. Alice has got this message of n-1 bits. She wants to transmit it to Bob. And what she's just going to do is she's going to add 1 extra bit, 1 bit at the end of redundancy, and that bit is going to be the parity, the sum mod 2, of her messages n-1 bits. So she'll just send her message, and then stick on the parity of the message at the end as 1 bit. So why is that a helpful idea? Someone over here? Okay, you're kind of over here, yes?
So basically there are 2 cases. If the original message was flipped, then the parity won't equal to the parity bit. And if the parity bit was flipped, then you know that as well.
Yeah. The idea here is that in this case, Bob can't exactly tell if one of the bits got flipped. You can divide it into 2 cases depending on whether it's the final parity check bit that got flipped or it's an original message bit that got flipped. But actually, in general, Alice's encoding always has the property that has an even number of 1s. Right? Because whatever number of 1s, even or odd, was in her message, that last bit she sticks on always makes it up to an even number. So now, I mean, it's good shape for Bob, right? Bob looks at what he sees. If he sees an odd number of 1s, he's like, well, one of the bits got flipped. And if he sees an even number of 1s, then he's like, okay, we're safe, nothing got flipped. Here we're definitely relying on the fact that he knows it's at most 1 bit gets flipped. If 2 bits get flipped, then he could see an even number of 1s, even though that's not what she sent. But, I mean, eventually we're going to handle more than 1 bit flip anyway. This is kind of for illustration. And actually, this is kind of optimal. You can try to prove this yourself. What's nice about this is Alice can send 2 to the n-1 different messages, only sending n total bits. And Bob has the ability to detect any 1-bit error. And there's no more efficient way to do this. Okay, so that's great. Let's try to up our ambitions a little bit. Let's take a linear algebra perspective on this as well. So you can think of Alice's message as n minus 1 bits. You can think of it as a vector in f2 to the n minus 1. And you'll see what both Alice do and what Bob do in this scenario is like matrix multiplication. If you think about it, what does Alice do? She multiplies this vector times this matrix G. In the in error correcting code terminology, this is called a generator matrix. And it's called that because, to encode a message, which is a vector, you just multiply it by this vector G. You may remember this matrix. It's the thing whose span was E. So it's really like Alice just takes a linear combination of G's columns based on what her message bits are. And you can see like what happens, the thing that she transmits, y1 through yn, is just you get x's values in the first n minus 1 entries. And then the last entry, yn down here, is like 1 times x1 plus 1 times x2 plus dot 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 mod n. So the last entry is the sum of her message bits mod 2. Sorry, I should have said mod 2. Okay, so Alice, in this case, really takes her message, multiplies by a matrix, and sends it over to Bob. That's what's going on here, this particular matrix. And actually, Bob's actions are similar. So let C be the set of strings that Alice might transmit. It's actually the set of all strings with an even number of ones. We called it E before, but we'll call it C here for code. C is just the span of the columns of G, because she can put down any message vector x. When she multiplies it against G, she gets some linear combination of G's columns. So C is, for example, a vector subspace of f2 to the n of dimension n minus 1. Now let's look at what Bob receives. Bob receives n bits. He also thinks of them as a vector. And remember, what does he do to detect an error? He just adds them up, mod 2, and checks if that's 0 or not. You can think of that as a very simple action. It's multiplying by this 1 by n matrix, which is called the parity check matrix, H. And if you multiply this matrix by this vector, you just get the sum of the entries of this vector. Everything is mod 2. So he just checks if that's 0 or not. And if h times what he receives is 0, then that means no errors. If it's 1, it means there was an error. Actually, Bob and Alice both multiply by matrices. And this is like, actually, all codes are based on this principle. Almost all codes that are used in practice are based on this principle. Alice takes her code as a vector, multiplies it by some matrix to make it longer, sends that to Bob, and Bob kind of checks if he got a good transmitted word by multiplying by a parity check matrix. So let me give you this more tricky question. What if we want to actually correct the error? I mean, if you detect that there's an error, you would prefer to know which bit got flipped. And so far we have a trouble, right? Because if Bob sees, let's say 100000, that has an odd number of 1, so there is definitely an error. But he doesn't know if it was this message, this message, this message. Any one of these has 1 bit flip from what he saw. So I'll show you the simplest extension of this scheme where you can actually correct a bit of error. This is due to this old person called Richard Hamming. It's called the Hamming 7.4 code. It's very simple. It's a very simple scheme where Alice has a 4-bit message in her head she wants to send to Bob, and she's going to send it using 7 bits. So that's somewhat a lot of redundancy, 75% longer, but it's going to have a cool property. And she's going to do it by multiplying her 4-bit message by this weird matrix. You'll kind of see where this matrix comes from later. So she has a message which is 4 bits long, some vector x, 4 bits. She just multiplies it by g, and she gets a 7-bit vector. And that's what she sends to Bob. And if you look at carefully, the first 4 bits of the vector that she sends are just her message. So she sends her message, and then the last 3 bits, which come from these rows, are certain parities of her message bits. So it's like she's using more parity checks in a sense. So this is the interesting property of the matrix G. Let's say she has a message x, she multiplies by g, and she gets a code word y, which is length 7. If there's no mistakes, then y will satisfy several parity checks. I claim that whatever she sends, if there's no mistakes, if you multiply it by this 3 by 7 matrix, you'll get 0. And the reason for that is, if you look, h times g as matrices gives you the 0 matrix. You have to check that, but if you do this matrix times this matrix, you get all zeros everywhere. So that means if there are no errors in transmission, and when Alice is sending x, she sends g times x, and then if you multiply that, y, by h, you'll get all zeros again. Okay? So it's kind of like a generalization of the scenario before. The last thing I want you to notice, this interesting property, is that this matrix G is a bit weird, but this matrix H is very nice. Its columns are just the numbers 1 through 7 written in binary. It's like 1, 2, 3, 4, 5, 6, 7. Okay? So here's how it works. Alice, I told you what she does. If she has a 4-bit message, she multiplies by this generator matrix G and sends this 7-bit result. Bob gets some vector out, z, which has length 7. Now, it might have some corruptions in it. It might have some bit flips. But whatever, he's going to just do this parity check. He's going to multiply h times z. Let's consider 2 possibilities. First possibility is that there are no errors in transmission, so that z is just what Alice sent, g times x. Now, as we saw before, h times g is all zeros matrix. So h times z is h times g times x, which is 0. So it's just like in the earlier case. Bob multiplies by h, and if he gets the length 3, 0 vector, then he's like, great, there were no mistakes. On the other hand, suppose that when Alice transmitted g times x, one of the 7 bits got flipped. We don't know which one, but one of them got flipped. And you can model that as saying the transmitted word z is gx plus ej. This stands for the vector that has a 1 in the jth coordinate and zeros elsewhere. Okay, so gx plus ej mod 2 is just like gx with the jth bit flipped. So now what does Bob do? He multiplies what he sees by h. He gets h times z, which is h times gx plus ej, which is hgx plus hej. We have the distributive property. And hgx is 0, so he just gets h times ej. And if you think about that, h times the vector that's all zeros except for the jth entry, that's just saying, give me the jth column of h. So what he gets out is the jth column of h, which is just the binary representation of j. So if he does h times z and sees 1, 1, 0, he knows that it was the 6th bit that got flipped. He immediately recovers j. So Bob can not only detect an error, he can exactly pinpoint where the error was just by seeing what answer he gets when he does h times z. Okay, so there's a generalization of this to larger messages. If you want to send 7 bits, you can do it with, if you want to send, what we just saw is you can send 16 different messages using 7 bits. In general, you can communicate one of 2 to the n over n plus 1 messages using n bits, and guard against 1 bit of error using an analogous scheme. And this is also optimal. This is something that you can prove for yourself fairly easily too. Okay, I'm out of time, so see you on Thursday. Yes.